Oh, yes, we are on membranes, but what part? Because we were not able to finish the membranes. What was that? Was it specific transporters? Facilitated diffusion?
So transport certain dog.
Ha? Ano? Ito ba? Tapos na ba itong ping-pong?
Done na po, Doc.
Ha?
Ano na yun, Dok?
Tapos na?
Tapos na nito.
Okay. How about this one? Tapos na rin. Ion
Yes,
channel.
Doc. Yes, Doc.
Yes, dog.
Okay. Okay. This one. This is still ion channel. Or this one. Still another ion channel.
Yes, Doc. Tapos na po ito.
Ionophores.
Done na rin dog.
Yes, Doc. Done na po. Yes, Doc.
Aquaporins. All right. How about this one?
Oh,
Active
hindi rin
transport.
pa, Doc. Oh, wait.
Okay.
Done
Tapos
na.
na?
And done.
Done. These types. Okay? Tapos na.
Yes, Doc.
Sodium, potassium, ATPs. Tapos na rin.
Yes, done.
This one. 3 sodium out, 2 sodium in, 2 potassium in, 3 sodium out. This is the inside of the cell. 3 sodium out, 2 potassium in. This is your sodium, potassium, ATPs pump. So as you can see here, 3 positive ions out, 2 positive ions in. So there is always lacking of positivity inside. Now, lacking of positivity inside. Because you are removing 3 sodium out, but only 2 sodium in. And the sodium and potassium have only one positive charge. No? So there is always lacking of positivity here. Okay? Transmission of nerve impulses involves ion channels and pumps. So ion channels, we have that, and then pumps. Just like your ATP's pump, which is mediated by energy. So ATP is being used. Transport of glucose. Are mediated by glucose transporter or GLOTs. There are 5 GLOTs. GLOT 1 up to 5. GLOT 1, GLOT 2, GLOT 3, GLOT 4, GLOT 5. Okay? GLOT 4 is for adipose tissue and skeletal muscle. So that uses GLOT 4. So these two tissues, adipocytes and skeletal muscle, uses GLOT 4 so that glucose can enter. Okay? All right, so we have here types of GLOTs, no? This one is, you are of course familiar already with this term, symport. Glucose comes in together with sodium. Okay, that is its import. Now, if it is only one, that's the only port. And you know what is this? This is an antiport. Sodium gets in, this one, potassium goes out. So no sodium can get in unless potassium can go out. Or no potassium can go out unless sodium can come in. Okay, so these two are dependent upon this sodium potassium pump. Dependent, because as you can see, this one requires sodium together with glucose to come in. So if you are putting out the sodium out, they're putting out the sodium, then sodium now comes in with glucose. Okay. All right. Endocytosis and exocytosis. Okay, for these are large molecules, so macromolecules, like polysaccharides, proteins, polynucleotides. Okay. Endocytosis involves ingestion of parts of the plasma. Sometimes endocytosis is also called cell drinking. The cell is drinking. Okay. All right, so we have it here. As the extracellular space, this is your membrane. Then there is invagination. And the cell membrane, the opposing cell membrane here, will close that one until once they are joined together, this is going in. Now, look at that. So, endocytosis, ingests part of the membrane. So part of the membrane here. So you see the membrane here. So part of it is ingested. Okay. There's another form, because this is known as fluid phase pinocytosis. And the other one on the other side, this one here, absorptive receptor mediated endocytosis. Now the thing here is that the invaginated portion has proteins like a brush. These are what you call your clathrin proteins. Clathrin. What is that? Oh, here. Protein clathrin. Okay. So, again, as part of that, similar to this, they are going to join together, and then you have a vesicle lined with clathrin proteins. There. So that is your cell drinking or pino. exocytosis. Now, exocytosis releases certain macromolecules from cells. Most cells release large molecules outside. So this is through exocytosis. Oh, here is a comparison between exocytosis and endocytosis. So these are the molecules that has to be extruded out of the cell, and then it has a membrane, very similar to that, so that it will join, look at this, it will join the membrane, and then extruding out what it contains. So that is the opposite of where is that? Okay, so this is the opposite of invagination, where it forms a vesicle and then you still have the membrane here. Now this one is the molecules to be extruded out has to be inside a vesicle in which the membrane of that is similar to the membrane here. Your cellular membrane, so that this membrane that encloses the macromolecules can become a part of your cell membrane. Okay? Now this is endocytosis. Membranes here, the same membrane. And this pinch off, that this forms now. Of course, this will open up where it is utilized, the molecules inside. And what happens to the membrane here will be degraded into phospholipids, fatty acids, amino acids, and will be material used again for forming membranes. In here, your cellular membrane. You get that? Okay. Molecules released by the cell surface, as it is there, becomes part. They can become part of the extracellular matrix, for example, collagen and glycosaminoglycans. No? This one here can be part of the glycosaminoglycans. They can enter extracellular fluid and signal other cells. Insulin, parathyroid hormone, and the catecholamines are all packaged in granules and processed within the cells to be released on appropriate stimulation. Okay? And of course, the opposite, the materials from the outside getting inside will be utilized. This could be glucose, this could be amino acids, short peptides. Okay. Various signals can be transmitted, signals such as neurotransmitters. So there are molecules that can act as neurotransmitters. And then, of course, hormones and immunoglobulins. They bind to the integral transmembrane receptor proteins, and they can become transmembrane signaling signal transduction. Okay, let's look at this. Gap junctions. What are these gap junctions? Now, in between cells, two adjacent cells, they can exchange materials through gap junctions. Now, imagine you have two cells near each other, and imagine that there is a pipe from one cell to another. So this pipe from one cell, materials from one cell can go to the other cell, or from the other cell towards to this cell here. No? Okay. And this gap junctions is formed by connexins forming a bihexagonal structure. Bi meaning two hexagonal structures. So there are 12 structures. And that structure are proteins. So 6 connexins from one connexin from the other cells. Okay? And then they form pipe that I was telling you. So it could be a pipe. So here it is. Here is one cell. And the other one down here. Okay? Cells, those are only just a portion. No. One connexin is made from two hemiconnexons. Each hemiconnexon is made from 6 connexin molecules. Small solutes are able to diffuse through the central channel when open, thereby providing direct mechanism of cell-to-cell communication. So they can communicate here. Their communication might be just fluid or some solutes or materials that is needed, or it could be a molecule that signals activation of the cell. So it also signals that one there. And this cell has also a connection to another cells so that that tissue could be stimulated or inhibited. It depends on what molecule passes through, whether that molecule can stimulate or can inhibit. Okay. Extracellular vesicles or exosomes represent a novel and previously underappreciated mechanism of cell-to-cell connection. Okay. Now here, this does not use the gap junction, but rather cells produces some materials that can be utilized by another cell, no, through kinds of receptors, like this one. This is the cell, source cell. The source will produces these materials here, also some materials, and then we have different receptors. So we have different receptors. So supposing this one here attaches itself, and this is an antigen. So these are different materials, no? Receptors will bind, and corresponding reaction of the cell once they bind to the receptor. Okay, so depending on the target cell, whether those materials are hormones, antibody on the target cell. Okay. Mutations affecting membrane proteins. The diseases, of course, that are formed here are not common. They're not due to mutations. Okay. So meaning to say, there is a problem with the LDL receptor. So the LDL could not be taken in by the cells because the receptor for LDL, there is a problem so that the LDL cannot bind to that receptor. So what happens? LDL will be roaming around in the plasma. And what does LDL carry? cholesterol. So that is what we call familial hypercholesterolemia. Familial because it is genetic. And the problem is the receptor. The receptor here cannot bind to the LDL, which carries cholesterol. You get? Now? So all are mutations. All are mutations. And as mutations are not common. Okay, so familiar. Usually, if the father has this mutation, the mother has also this mutation, naturally, the offspring has this mutation. Okay? Oh, continuation. No? So, hereditary spherocytosis. This is your RBC. Which is involved. Metastasis of cancer cells. Nocturnal hemoglobinuria. Nocturnal hemoglobin. So you are urinating hemoglobin. Okay. So these are, as we said, these are not common. No. Now, like for example, cystic fibrosis. There you are. This is common in North America and Northern Europe. No? Both of these countries have cold winter. Very cold. No? And what does that got to do with mutation? Cold countries. Families are usually sleeping together. Yes, in Europe. It is customary there to marry within the family. And so this brings about the recessive gene becomes dominant when the male and the female both have recessive genes. Their offspring, usually that recessive gene becomes dominant. Okay? Because it is customary there, no? Like, you know how it is. To preserve the kingdom should not be divided. Diba? And so that the kingdom will not be divided, then they marry within their family. Okay. So that is not happening with us. No. So, oh, kadagan baning thank you. Sama to. 13. Battery. Oh, battery running low. Okay. Let's go to ATP. And then, of course, plenty of energy, obesity. Where do you get your energy? The food that you eat. Okay. So in starvation, there's no food. In marasmus, there might be food, but the wrong kind of food. Oh, that is taken in marasmus, energy imbalance, as well as protein, no? Imbalance. And then obesity, there's plenty of food. So there is surplus of food. Okay. So let's start there to understand this. Energy procurement. Gibbs was the first one to coin this free energy change. This free energy change is named after the researcher Gibbs, no relation to Jano Gibbs. And this is symbol for free energy change, delta G. Okay. All right. That free energy change is that portion of the total energy change in a system that is available for doing work. Or that is what we call useful energy, also known as chemical potential. Okay. First, we must have to understand this laws of thermodynamics. Let's borrow these two laws from the engineers. Uh, so first law of thermodynamics states that the total energy of a system, including its surroundings, remain constant. Okay. So what do you mean by the system? The system includes you, all around you, or the entire Philippines, or the entire world, or the entire universe. That's the system. So if you go micromolecular from the cell, surrounding the cells, or anything that surrounds them, or its environment, is the system. Or you want to be astronomers, Earth, together with the planets, with the solar system, that's a system. And the solar system, our own solar system, is just universe, which that is included as a system. Now, when I was still a student, when we were talking about energy and our professor once told us that, no, ask us, how do you define God? No one could answer. How do you define God? And then we asked him, how do you define God? And he said, God is energy. Because everything is energy. Huh? Okay? Energy has no origin, no? Cannot be created, cannot be destroyed. But it can be transformed from one form of energy to another. Diba? So, I've read a definition of God. Since God has no beginning and has no end. So it is just like energy has no beginning and has no end. The energy how was the electrical energy made in Tungunan? It comes from thermal energy. And what is the thermal energy in Tungunan? It is volcanic steam going out from the bowels of the earth. And that thermal steam is used to drive a turbine. And when the turbine turns, it turns the generator. electrical generator. And the generator forms electrical energy and is distributed by transmission lines, and it reaches the global, and there you have electricity. So that electrical energy can be transformed into light energy as a source of light, or it can be converted to electric stove. Diba? Okay, so you have now understanding of what energy is. And the first law of thermodynamics says that total energy of the system, including its surroundings, remains constant. It is there. Okay? All right. The second law of thermodynamics that we have to understand is that the total entropy of the system must increase if a process is to occur spontaneously. What is entropy? Entropy is a state of disorderliness. State of disorderliness. So if you increase the disorderliness of a system, increase, a process is to occur spontaneously. So how can we, okay. We are not having a class where you are sitting down, and then just imagine that you have a class there, you are sitting down, you have your teacher in front of you, and because he is very strict, you do not even move in your seat, and you just listen to him. No? So that is an ordered entropy. You are all sitting down, doing nothing, just listening to your teacher. That's an ordered entropy. All of a sudden, somebody shouted from outside, and he says, "Fire! So no!" So everybody stands up and then rushes to the door. That is now increasing the entropy. You increase the disorderliness. There's so much disorderliness that you bump into your chairs, you bump into each other. So it is just like molecules in a chemical reaction. The molecules that is not disturbed, it's an entropy. Now, you must have seen this in your kindergarten chemistry, that if you want to hasten the reaction, you try to heat it in your Bunsen burner. No? Diba? So heat there increases the entropy of the molecules. The molecules gathers energy and it moves around. And we said no chemical reactions can occur if the molecules will not collide. Collision theory. Diba? So, if you increase the entropy, a process is to occur spontaneously. So if you have two molecules who have chemical reaction can occur spontaneously if they have high entropy. Right? Yes or no? All right. So let's try to, look at this. Under conditions of constant temperature and pressure. So under condition of constant temperature and pressure, you're not increasing it, you're not decreasing the temperature and the pressure also. The relationship between the free energy change of a reacting system and the change in entropy is expressed by the following equation. So free energy change is delta G. Delta H is change in heat or enthalpy minus temperature absolute is entropy. So free energy change is equal to change in enthalpy minus temperature times change or delta S, no? Change. Once you say this delta, it means change of entropy. But the problem in this is, how can you measure disorderliness? How can you measure disorderliness? All right. So let's go to the next one. Delta H is the change in enthalpy. And E is absolute temperature. In biochemical reactions, this approximately equal internal energy of reaction. So we change delta H to delta E because that is approximately equal. Change in heat is equal to the total change in internal energy, or delta E, minus absolute temperature and change in entropy. Okay? Now, let's go to what we call, again, let's go back. Again, we cannot measure this. So what are we going to do? We go to this one. So the standard free energy change can be calculated from the equilibrium constant of the reaction. Okay? So this is standard free energy change. So you get this superscript. That means so if what comes out, the action is exergonic. On the other hand, if delta G is positive, the reaction proceeds only if energy is supplied to it. And we call that when the magnitude of the positivity of delta G is high or great, the system is stable and there is no tendency for reaction to occur. If delta G is zero, then the system is at equilibrium. Okay? We have here an exergonic reaction, which is from point A going to point B, is what is called a downhill reaction, going down. The endergonic reaction is an uphill reaction. Uphill reaction. This is the analogy, Now, okay, just like going downhill, you don't need energy. Let's go that way. And endergonic reaction requires energy to go uphill, right? Okay. In our system, our cells, endergonic reaction that requires energy, usually couples with exergonic reaction, meaning whatever energy that is released here will be used to propel the endergonic reaction to occur. Okay? As you can see, there's a difference. This endergonic reaction does not go up there. No? This is only up there. So in our cells, endergonic reactions, these reactions is coupled to exergonic reactions. Exergonic reactions releases energy and the energy is used up for this reaction to occur. And there's a discrepancy, look at that. And that is released as heat. Going back to the body, this heat released in your system is used to have your body heat, which is 37 degrees centigrade. So that's plan of the energy released here later use or future use for an energonic reaction to occur. Okay? All right. Here is an oxidation reduction reaction shown here. Okay? We have a compound which is the reduced compound. Compound A is a reduced compound. It is oxidized and it loses your hydrogen. The acceptor of that hydrogen is another compound which we call a carrier, and the carrier now has this hydrogen. And this hydrogen has a final, final acceptor of hydrogen is compound B. And B accepts the hydrogen. This is oxidized compound. And then once it acquires the hydrogen, it becomes reduced, BH2. All right. Now, it does not mean that you have only one carrier. There might be another carrier before a final acceptor of hydrogen comes around. Now, this is an example of an enzyme or dehydrogenase. D meaning remove hydrogen. ASA means enzyme, no, dehydrogenase. So coupling of dehydrogenation and hydrogenation reactions by an intermediate carrier. So this is your intermediate carrier. Okay. So compound A, which is reduced, becomes now compound A oxidized. So oxidation meaning loss of the hydrogen here. And the gain of hydrogen makes the compound B, which is oxidized, becomes now reduced compound B. Okay? All right. And if you remember, let's go back again. We said every exergonic reaction that occurs, the energy is captured. No, being captured to be utilized for intergonic reactions to occur. Okay. What captures that energy is this compound, which you are familiar with, ATP. You have here adenine, which is a purine. You have ribose, which is a sugar. And then you have 3 phosphates. This bond between this carbon and this carbon is an ordinary ester bond. Okay? But this bond here, from phosphate to phosphate, phosphate to phosphate, you have anhydride bonds. Anhydride bonds. When you cut off this bond, you release energy. Or you cut off this bond, you release energy. Now, where is your magnesium stabilizing this two? Now, so this is what we call your energy currency, ATP, and its cousins, because you have cousins. Uh, you have your GTP, you have your TTP, you have your CTP, uh, UTP. Okay. But ATP is the one that does most of the job in uh, storing energy here. Now this is a table for high energy phosphates. Okay. Where is your ATP? It's here. When ATP releases one phosphate, it produces 7.3 kilocalories per mole. If the two phosphates are removed, you have 7.7 kilocalories that is released. See, now this one is kilojoules. No? But we are mostly using kilocalories. Okay. So the highest here is phosphoenol pyruvate with kilocalories of 14.8 or 14.7. Carbamyl phosphate has 12.3. 1,3 biphosphoglycerate, you have 11.8. Creatine phosphate, 10.3. Okay, and so you have your ATP losing 2 phosphate, 7.7. ATP losing 1 phosphate, 7.3. Below that, below your ATP are now considered as low energy phosphates. Low energy phosphate. Glucose 1-phosphate has only 5. Pyrophosphate removed from ATP is only 4.6. Fructose 6-phosphate is 3.8. Glucose 6-phosphate is 3.3. Glycerol 3-phosphate is 2.2. Ang sakit, tabunan man. All right. This is, these are low or high energy phosphates. So let's look at the high energy phosphates. Okay. So going back here, that's ADP. That's already one phosphate. To make this into ATP, so you get a phosphate higher than 7.3. So you may use phosphoenol pyruvate, you may use creatine phosphate, which is in the muscle, no? So that's 10.3. You can create that phosphate and add to ADP to become ATP again. So that the reaction goes this way. So you must have a high energy phosphate. And that high energy phosphate, you can get it from here, from here, from here, from here, or even from here. Because that's already 7.7. So you can add that one phosphate to ADP to become ATP. Or you can get this phosphate here to add to ADP to become ATP. That's high energy phosphate. Those below this cannot replace, because that's only 5, that's only 4, it's 3, that's 3 here, that's 2. Cannot replace, those phosphate cannot replace the phosphate that is lost in ADP. Can you get that? Huh? Okay. This, what do you call this sign? Anybody? This is in your computer. You have that sign there in your computer, di ba? In your keys of your computer on the left side, below escape. You do not know? That's a tilde sign in your computer. But this sign in your bioenergetics, this is known as the squiggle. Squiggle, that one, means high energy phosphate bond. High energy phosphate bond. Look at this. This phosphate here does not have a squiggle. That is just an ester bond. Okay? All right. All right. When ATP donates its phosphate there, ATP becomes ADP. So this is how it looks like. -1 phosphate here. I have here 1, 2, 3. This has only 1, 2. Okay. The phosphate release is stabilized by the formation of resonance hybrid in which the 3 negative charges are shared between 4 oxygen atoms. Okay. Here you are. ATP acts as the energy currency of the cell. So what is our Philippine currency? Peso. Very good. American currency is the dollar. No? All right. So, our currency for energy is ATP. Huh? So this is how the cell use. They do not use peso or dollar. They use ATP. Okay? Oh, here is now how your ATP is being used in the ATP cycle, ATP cycle. Okay. ATP cycle. All right. So you remember this? Creatine phosphate. Diba? Phosphoenol pyruvate, 1,3-biphosphoglycerate, all they produce high energy phosphate bonds. And they are utilized to add to ADP to become ATP. To become ATP. And this ATP is being used for phosphorylation reaction. Adding to glucose becomes glucose 6-phosphate. Adding to glycerol, glycerol 3-phosphate. To glucose, to add 2 phosphates, 1,6-biphosphate. And other phosphorylation reactions and endergonic processes or reactions that cannot occur unless energy is supplied. Right? So that high energy is added to your creatine here becomes creatine phosphate. And you have that storage of creatine phosphate in your muscle. So that when the muscle contracts, creatine phosphate is released because every time the muscle contracts, ATP is used and you produce ATP. And to regenerate that ADP, that phosphate from creatine is added to ADP to become ATP again. And these are your sources of high energy phosphate bonds, oxidative phosphorylations. Okay? All right, 3 major sources of high energy phosphate taking part in energy conservation or energy capture. First is your oxidative phosphorylation. This is in your respiratory chain. You know what your respiratory chain? No? You remember in your class in your kindergarten, you were told that there are 2 kinds of respiration. You have external and internal respiration. External, you can observe it, your lungs are expanding and deflating. But your internal, you cannot see it. The internal respiration is the utilization of oxygen now to become water. And this is through your respiratory chain or electron transport chain. So this is inside your mitochondrion. an organelle in the cell. So that becomes internal respiration. So our in our schedule, we will be talking about respiration, the block on respiration, physiology and biochemistry. Respiration. So this is the respiratory chain or electron transport chain. Okay. So another source of high energy phosphate capture is glycolysis. Innate formation of two high energy phosphate results from the formation of lactate from one molecule of glucose generated in two reactions catalyzed by phosphoglycerate kinase and pyruvate kinase, respectively. Okay. You are also told in your kindergarten chemistry that there are two kinds of glycolysis. Aerobic and anaerobic. Aerobic glycolysis produces more than two high energy phosphates. So this one is anaerobic because end product is lactic acid. Okay. And the third is citric acid cycle or Krebs cycle or tricarboxylic acid cycle. Citric acid cycle. Okay. Oh, here are reactions. So this is a reaction that is found in your muscles. The muscle contains creatine. And if there's plenty of ATP, because you are well fed, this creatine are converted to creatine phosphate, in which you have a high energy phosphate there. And this is stored in the muscles. So when the muscle is contracting and ATP is low, the creatine phosphate are now being utilized to phosphorylate ADP to become ATP. Okay? All right. Here's another reaction. Glycerol plus ATP or adenosine triphosphate catalyzed by glycerol kinase. Whenever you have an enzyme that ends in kinase, that means phosphorylation reaction. Phosphorylation reaction, meaning a phosphate is added. So here is glycerol, an ATP. Through a kinase, glycerol kinase. So you have now glycerol 3-phosphate plus the remnant of ATP, adenosine diphosphate. Okay. ATP allows decoupling of thermodynamically unfavorable reactions to favorable ones. So that is your endergonic reaction requiring energy, and the energy that is being used comes from ATP. Okay, so this is glycerol phosphorylation, no, utilizing ATP. There you are. So you have now glycerol 3-phosphate. This becomes now a reactive compound, glycerol 3-phosphate. This one is not reactive. Glycerol 3-phosphate is, because it's on the number 3 carbon, the phosphate is in the number 3 carbon, so glycerol 3-phosphate, it becomes a reactive compound. Okay. All right. So ATP allows coupling of thermodynamically unfavorable reactions to favorable ones. So look at this. EMP loses already 2 of its high energy phosphate, sodium phosphate. It reacts with ATP. So 1 phosphate is added to that, and that makes it ADP. So we have now 2 ADP. This is catalyzed by adenyl cyclase. Adenylyl cyclase. Oh, cyclase naman, I'm sorry. Adenylyl kinase. Adenylyl kinase is important for maintenance of energy homeostasis in cells because it allows 1, 2, 3 group transfer potential and ATP to be used in synthesis of ATP. AMP forms as consequence of activating reactions ATP to rephosphorylate to ADP. AMP to increase concentration when ATP becomes depleted so that it is able to react in metabolic as a signal to increase the rate of downhill reactions. Downhill reactions or exergonic reactions is catabolic reactions. Reactions that produces energy, which in turn lead to the generation of more ATP. Now remember, catabolic reaction releases energy and it is captured in the form of ATP. The opposite of that is anabolic reactions or an uphill reaction. Anabolic reactions require ATP so that anabolic processes will proceed. When ATP forms AMP, inorganic pyrophosphate is produced. Sa ulit pag sakas taas. When ATP forms AMP, inorganic pyrophosphate is produced. ATP can also be hydrolyzed directly to AMP with the release of PPI or pyrophosphate. This occurs, for example, in fatty acid. ATP plus coenzyme A plus a fatty acid or organic acid R, COOH. This is a general formula for organic acids. Now this is a coenzyme known as coenzyme A. Okay? Activating this fatty acid, because fatty acid are usually inert, is to add a phosphate. No? Add a phosphate or add a coenzyme A. But this requires energy coming from here. So we have here acyl-CoA synthetase. So the fatty acid, this one, is here with the coenzyme A attached to it. And what is spent? Two high energy phosphate bonds. Pyrophosphate is removed from ATP, so that ATP becomes now just AMP. See, this is activation of fatty acid. Before you can utilize your fatty acid, it must be activated by adding a coenzyme A, and that would require ATP. And the energy requirement is high because your ATP becomes AMP. The two phosphates are removed. Okay. Now to split this, you need a pyrophosphatase to split this to form more energy. Okay. A combination of the above reactions, what that we're talking about, makes it possible for phosphate to be recycled and the adenine nucleotide to interchange. Okay. You have your acyl-CoA synthetase that produces your fatty acid CoA. All right. That uses up ATP, releasing pyrophosphate. Pyrophosphate is acted upon by pyrophosphatase. So it is broken down to inorganic phosphates. And these inorganic phosphates then can be utilized to form into ATP again. Now, with ADP plus a phosphate, that becomes ATP. All right. Other nucleoside triphosphate participate in the group transfer. Okay, like for example, UDP, uridine diphosphate. This is what they call cousins of your ATP. This phosphate is added to it, so it becomes UTP, becomes ADP. And the enzyme is nucleoside diphosphate kinase. Okay. Are you still awake?
Yes,
Oo
Doc.
daw.
Ako daw.
Yes
Oo.
daw.
Okay. How many hours have we had already? 1 hour and a half already?
1 hour
Yes,
47.
Tired na?
Yes,
Are you tired? Ha?
Yes, Doc. Gutom na, Doc.
Ha? Saturated na? Saturated na ang breast?
Yes, Doc.
Super saturated.
Sige. So,
Utason na, Doc. Utason na.
ha? What?
Thank you, Doc. Na, Doc.
So we'll just continue chapter 12 next time.
thank you, Doc.
Sige. Hinay-hinayon talang ni.
Salamat daw.
Thank you, Doc.
Thank you daw.
Thank you, Doc.
Thank you, Doc.
Thank you. Welcome.